じゃあ、today's content ですね。Sensor start is separated into two classes, but to Pi it is separated into two classes. Last week is about fat, and today's content is about what it is. No response. Hi, what is the response about Pi separated into two classes? First class is about fat, second class is mainly about fat.
External and internal.
Ah, yes, that's right. The first class is mainly about the internal sensing, and today's content is about the external sensing. Internal sensing, internal sensor and the external sensor. Internal sensor is mainly detect the inside of that object, internal state of itself, of robot system or something, like the joint position, joint moving speed, using for the feedback signal, used as a feedback signal for sequential control and so on. So the understanding about itself is very important to control its body, its movement. For example, the sensing the gravity and the slant angle is measured. Slanting angle is measured. So the understanding about itself to control the moving of itself more smoothly, more useful, more rapidly, and so on. And then the external sensor is to understand environment, because the robotic system has a physical body, and also the most important part of that work is the interaction between itself and the environment. And then by using some interaction, some task is carried out. Work object and work environment, and or relationship between the robot and the external world is detected and recognized. And the grasping force of objects, of grasped object. So therefore, it is used to control the grasping force based on the object features. For example, to holding something, and the grasping force control is very important to grasp firmly or carefully. To grasp this kind of flexible object, or this is kind of hard object, the type of grasping is different, should be different. So the target something to understand is very important to control. So, before that, what is a sensor? Sensor device, sensor means the device or module or subsystems where state of measuring object is translated into the physical or chemical quantity. So the measure means in the engineering viewpoint, sensing is the measure something, detect something to understand, and mainly it make some quantity, for example, in some values, to make it values. For example, in this, the temperature or humidity is understood as some degree or some percentage. So to control it. So the measurement means some making into, understand into some values to control it. The internal sensor and the external sensor. So last week content is about the internal sensor. And then today is mainly about the external sensor. And most of you is maybe from some data processing, some software. So therefore, maybe you are interested in about the sensing part. For example, in the environment understanding. So, ちょっとroughly watching. どうしてこれがこんなにちょっと面白いんですか。 Look into some outlines firstly. So, まずは何だ First part is vision sensor って書いてある。vision sensor ですね。それからなんかtactile sensing 書いてありますね。tactile sensor vision sensor でtactile sensor でand the distance proximity sensor displacement とかdistance sensor とか書いてありますね。distance sensor ね。これdistance でRGB カメラとか書いてあって、あとなんかフォースセンサーでフォーストルクセンサー is used as a assembling task of industrial robot という意味でこう書いてあるんですね。というわけです。OK ですね。で、ちょっと待ってね。まずはビジョンか。ビジョンパートは何ですかと言ったら、ちょっとビジョンパートは、プリンシプルの話ですね。フォトエレクトリックエレメント。で、フォトエレクトリックエレメントは、なんか、some material emits electron, then receiving some optical energy で、だから、optical energy is applied and the electron can be generated. So, this electron is measured. フォトボルティックエフェクトっていうのは、このフォトダイオード、フォトトランジスタ is based on this principle. The photo is given here, some current is the light, is irradiated light. And the transistor is some kind of switching circuit to when the light is detected. And photoconductive effect っていうのは、some light is given here, the conductance or the resistance will be changed. Conduction electron is increased with optical energy and internal resistance is changed. されてますね。Some kind of CDS, cadmium sulfide cell, is detecting the light, changing its resistance. Based on these kind of principle, this kind of, for example, maybe you have tested about the line tracing robot. So using the photo detector, like here, the light is emitted and the reflected light is received by this sensor. Or emitting and receiving. Emitting this and detecting this transistor, and the sensor output is here. By using this, the wall detecting and the white part, black part detecting by using this kind of robot to control the tracking the lines. Okay, you may have tried like this. And make it two-dimensional. The image sensor is like this. The image pickup tube right here, and the color image sensor is 3 light is used, but mainly 1 light detected or not. So by using this solid state image sensor, semiconductor image sensor using the photodiode, this is divided into 2 types, CCD type and CMOS type. CCD タイプ and CMOS タイプで、ここに CCD タイプメソドロジーとかアドバンテージ、ディスアドバンテージ is given here. CMOS タイプ is like this. Firstly, the CCD is mainly used because of its high performance, but it is a little bit expensive to detect this CCD device. So therefore, the CMOS device is very useful because it is easy to produce, it is easy to be manufactured, and the performance become increased. So therefore, presently, the CMOS sensor is widely used. And the 3D image sensor, the one way is it is divided into two types, passive sensor and active sensor. Passive is only some lighting condition is detected. The passively lighting condition is detected.イメージセンサーは、イメージセンサーっていうのは何ですかって言ったら、イメージセンサーは、ライトのデンシティですね。デンシティ is detected。だから、ブライトネスだ。ブライトネス is detected。ね。だから、ダーク or bright。ダーク or bright。dark, too bright. It's detected. And the color sensor is only using the color filter is used. Filtering by using this filter, the common light, income light is natural light. And the RGB, red, blue, green, is a main three color to make the natural light. By using these three colors, combination of these three colors, natural light is reproduced. So therefore, the detection part is also the three light is detected. To detect the three light, the color filtering method is necessary. So therefore, by red filter, the red light is detected. The green filter, green light is detected. By using the blue filter, blue light is detected. But in any way, the detection is only the brightness is detected. Dark or bright is detected. で、何を言ったかというと、いいか。で、passive light sensor. The passive light is only the detecting the brightness. In some cases, color brightness is detected. To make it three-dimensional, the one single camera, monocular camera's method is changing its position, the shading from the focus and the shading and motion by making it moving. The three-dimensional object is detected. Ambulatory visions, dynamic picture image is there. One of them is SFM. Afterward, I will explain. And the multiple camera system, mainly about the binocular visions. It means stereo visions. Two cameras is used to other viewpoint. So one object is detected, and then the three-dimensional image can be reproduced. And another way is active sensing. Active stereo means the active lighting pattern is produced, and then this pattern is how to find this pattern is working is detected. Pattern projection and space coding looks like this. Some pattern is projected, one projector, and then the camera is detecting the structured light image like this, and then this space code can be detected, and based on this space code, some object shape is estimated. Another なんかこれ light selection method とか multi point projection method とか、まあこれはlight section method は this kind of slit light is given from the laser generator, and then how to this slit light is shown by this camera, and then based on this light shape, this object is the shape of this object is detected. ちょっとなんか、見ますか？これか。なんかパターンがプロバイデですね。で、カメラでディテクティング。Next, だから、but basically stereo vision is like this. Stereo camera vision は two camera is in this case parallelly it is watching the two cameras. One camera and the other camera is here, and this light lens is here, detecting the in its front, and one object is here. From this part, the light is come from. This is the focal point of this camera. This is the focal point of this camera, and then the two-dimensional camera. Two-dimensional camera. What is the meaning of two-dimensional camera? The pinhole method でね、なんか pinhole method, and then the three-dimensional sub-object. Three-dimensional sub-object can be detected in a single camera. でしょ? What is the meaning of this 3D? 3D object and pinhole. Pinhole is here. The camera is here. Camera means it is projected to 3D, 2D projection でね。It means 3D object is projected into the two-dimensional plane. Two-dimensional plane. ね? なんか general 3 object in the environment is through this focal point, pinhole. It is projected here. まあなんか triangle part and some object part is projected into two-dimensional plane. It means. And then in this two-dimensional plane, for example, it is separated into some lattice part, and each lattice, each column, how density it is. ね。How brightness it is detected. So this is the main meaning of the camera. Yeah? Three-dimensional world environment is projected into the two-dimensional, and from this, for this two-dimensional plane, what is shown on this plane, and each columns, each matrix part is the brightness is detected. This is monocular camera, but by using some color filtering, three filter is used in each two-dimensional. For example, the red part, green part, blue part is detected, and by combining these three two-dimensional images, and then the color is understood. Is a way. And the stereo camera is also here. The three-dimensional environment is projected into this is a left side cameras, two-dimensional, right side camera, two-dimensional. It is projected here. And then the stereo vision means the sum part of three-dimensional position is estimated by using this information. This information. So on this, the left camera screen, this point is projected here. The right camera's two-dimensional screen, the three-dimensional position is projected on here, the two-dimensional position. So therefore, by using this two-dimensional position and this two-dimensional position on this screen, but the space free, the three-dimensional environment, this position is XY coordinate, and this length ZL is the F, ZR is also the L, but this point is XR, YR here, okay? And this point is for this screen, the XL and YL is here. Okay? The coordinate value on the right camera image is right here, and coordinate value on the left camera is right is here, left is here. And by this, based on this position, 4 parameters, the position of the three-dimensional position, the target point position is here. This is the main three-dimensional basement coordinate is here. Position of the robot coordinate. The robot means this is the robot coordinate, for example. Origin position of the robot coordinate PO, and from PO, this position looks like this. The meaning of these 4 information, these 4 parameters, we want to find this three-dimensional position is the main work of the stereo camera. So this XO, YO, 0 is XY, XO, YO, 0 is looks like this coordinate. But it is very simple, it is easy to understand by using some projection でね。別にこんなの、ここのライトで例えばこのポジションがこうで、このトライアングルで maybe it is easy to find this position とかいうやつだよね。So by using this, you may be able to find these equations. This is one work of today's subject. Okay, you have to write this firstly, this coordinate, and please explain the coordinate, each of the coordinate. This is the robot coordinate, this is the camera coordinate, left camera coordinate, right camera coordinate, and from these parameters, you have to understand this, and then this is equations like this. You have to find the later. And by using these principles, three-dimensional understanding, it is practically used. For example, the assembling some engine is assembling into the car chassis, and also to make the hole to positioning of this, and then some window hole is also detecting like this. Body assembling, the body positioning, and the whole positioning is also detecting by the practically. This is a practical way. And not only the automobile assembling, But also this kind of three-dimensional technology is also by using some human motion detection. In this case, marker is put on the typical point of the joint angles, joint position, ankle position, the knee position, the waist position is put it on. And then the camera surrounding here, this camera is surrounding here. And then this person's motion is detected. And then by using this two-dimensional camera's image is combined, and then the three-dimensional position is detected. The marker tracking method, high precision and three-dimensional, and the dynamic calibration method, the short setup time. Yeah, it's okay. Then you can find this system like ちょっとオプティトラックっていうのを見てみますか。これマーカー is put on here. これ41カメラ is set on. Camera is here, surrounding. This kind of technology is used for the capturing the motions, human motions, and then it will be used for the game character movement or some virtual person's object movement in the movie, theater movies, and so on. This technology is used. Well, high speed capturing is also very important, and as I said, the structured from motion is the one object is detecting in the different conditions, different positions. The object was watched from the different positions, and then based on these multiple two-dimensional images, three-dimensional object is reconstructed. Its structure from motion is because the camera is moved and taking the picture in the different angles, and then the three-dimensional object is reconstructed. これは例えば structured from motion pipeline. Taking a lot of image of an object って書いてあるんですね。オブジェクトのイメージをたくさん取って、で、ここでなんかフィーチャーポイントエクストラクションして、フィーチャーポイントエクストラクションで、フィーチャーポイントマッチングすると、3D-dimensional object is reconstructed っていうやつですね。Identify point in the image that can possibly be detected in the other image で、だからフィーチャーエクストラクションですね。で、フィーチャーエクストラクションでマッチングして、で、3D-dimensional is estimated. For feature point, pitch point is corresponding each other estimation, and then the 3D point position is the estimated. で、これワンオブジェクトで、the other オブジェクトで、これをだんだんマッチングさせていく。で、そうするとなんかポイントクラウドができて。3D-dimensional ポイントクラウドをリコンストラクトして、で、それぞれのポジションにカラーをパッチすると、some kind of 3D-dimensional object is reconstructed. これはだから、これビューポイントですね。たくさんの many view point is here. で、afterward you can try to compute って言って、このパートをこうパッチすると、なんか looks like this kind of three-dimensional object is reconstructed like this っていうのが、これが、まあ、カメラの1ポジションですね。っていうのが、 structured from image ってやつ。これね。それからビジュアルスラムっていうのもあって、スラム means the simultaneous localization and mapping っていう、localization meaning the camera's position is estimated, but mainly the map development, three-dimensional map development is the main work of this SLAM, and also the file making the maps, the localization, the sensor's position is also estimated. So this technology is very important to make the environmental map, construct the three-dimensional environmental map. And firstly, the SLAM technology is developed by using the range sensor, range scanner, the distance sensor based. But afterward, the two-dimensional vision-based sensor is visual SLAM. It is called visual SLAM. Only the visual image, and then the reconstruct the map, and the camera's position is also simultaneously estimated. So ちょっとこのビジュアルスラムっていうのもなんか見ますか？カーナビゲーションってありますか？これ見てますか？これだからキャプチャーイメージですね。で、こういう、フィーチャーポイント取って、フィーチャーポイントを取ってって、これだったら今、なんか GPS data is also used to detecting the camera's position, of course. And then this kind of three-dimensional map is gradually constructed. The GPS はつまりgyro and GPS sensor is also mixed to localizing the camera position. で、このイメージをくっつけて、で、if it is loop is closed, this image, this three-dimensional map is also more sharply detected. こういうのビジュアルスラムってあるからちょっと見てみますか？ビジュアルスラム。これはこのカメラで、detecting the environment でこのフィーチャーポイントエクストラクションしていて。surrounding to create the environmental map と書いてありますね。で初めはこうポイントクラウド、フィーチャーポイントのポイントクラウドで、from the point cloud からこのロボットポジション is estimated。これはリアルセンスっていうセンサーを they are using。はい、っていうようなことがありますね。これ this kind of work is very you may be interested in like this kind of this is a vision technology and also the vision post の前にどっちも見ますか？これはこっちかディスタンスセンサーの方か。ディスタンスセンサーはディスタンスセンサーなんかリプレイスメントセンサーとか例えば PSD っていうセンサーPSD is a one way to detect the sensor when the distance is changed. The output voltage will be changed, so therefore the distance will be estimated. This is a one-dimensional sensor about the distance sensor. And the プロダクトだとパナソニックとかありますけど、ね、何を見たいかというと、それがディスタンスセンサーで、ディスタンスセンサーだけど、ディスタンスセンサー is the firstly equipped on this kind of vehicles, UAV or the AVG, autonomous vehicles that carrying some object in the factory or moving. And then the two-dimensional, this is the two-dimensional scanning the laser by using the laser light. The distance is detected, and then this is the industrial robot. And for the safety, the approaching human is detected by this sensor to find the safety degree or the dangerous degree is detected. So this kind of two-dimensional scanning sensor, scanning laser sensor, is firstly widely used. This is a DIC Corporation's sensor. And then this is a Japanese sensor. The Hokuyo automatic is also the detecting. This is a small sensor to. これ見てみますか。ちょっとこれあんまりよろしくない。やめよう。こっちのジックのセンサーのデモビデオどこかこれか。ない。ショートビデオこれとか。
TIM300 from Zik. Indoor laser scanner for anti-collision protection and presence detection. TIM300. So small, so simple, so affordable. Perfect in detail. Brilliant overall. So small. At only 7.9 centimeters in height, TIM300 fits under every pallet. And at only 150 grams, it's light enough for use for stationary or mobile applications. And despite its compact size, the TIM300 is tough enough to withstand a few knocks. The reason? A robust housing made of die-cast aluminum and shock-resistant electronics. So simple. TIM300 is ready to go in 5 minutes. Up to 16 field sets in 3 different field shapes can be chosen easily and intuitively. This includes rectangles with various dimensions, which can be chosen through the binary combination of the 4 inputs. And radial fields with a wide range of sizes and angles. Or segmented free shapes with corners that can be freely chosen.
これはだからエリア決めてて、ここはセンサーね。で、scanning around here, and then the area is the preliminary decided. This is a ちょっと weak dangerous area, the little bit dangerous area, and the severely dangerous area. It can set in the 3 areas for the warning levels. It become different, and then the worker is approaching this part. So some dangerous machine is working. So it can be settled. というやつですね。
According to your requirements, TIM300 is the first sensor of its class that can be programmed using touch and teach without the need for a PC. When the teach push button is pressed, TIM begins to scan its surroundings and then saves the measured field shape. The difference between fields 1, 2, and 3 increases in increments of 25%. Of course, programming can also be done with a PC by using a USB connection and SOPAS, the universal software for all Zik devices. So affordable. Depending on the form of the protective field, a single TIM300 can check an area of up to 37 square meters, a scanning range of 4 meters, and the extremely wide scanning angle of 270 degrees makes it possible.
まあいいや、というのはスキャニングセンサーという意味で、2-dimensional scanning sensor. The laser range scanner is here. で、by using these sensors, the mobile robot is operated the SLAMS technology. ね、で、for example, the 例えば、Autonomous Navigation for the Mobile Robotics Challenge 2014. Let's look at this. これちょっと早すぎてわかんないか。これちょっとダメだな。ちょっとこれもよく見て。Autonomous Mobile Robot、これかいいか。はい。筑波ユニバーシティですね。で、まあ、ステレオカメラとか使ってますよとか、レーザースキャナー is equipped、まあ、LCD ディスプレイとか書いてあるんですけど、で、IMU も搭載してますよとか、で、PC が入ってますよとか言って、で、なんかモバイルロボットで、で、筑波チャレンジっていうのは、some courses the preliminary decided and courses moved the autonomously. But to the preliminary, the environmental map is prepared by trial movement. で、trial movement から、and based on that preliminary decided map is created the SLAM technology. Localization using the line. And then when the executing the movement, the all surrounding is the real-time tracing, and then the some marks, the landmarks can be detected and matched, and then this present position is slightly modified based on the map, the tree landmark って書いてあるんですよね。The map is based on the preliminary prepared three-dimensional map and the landmarks. The present position is localized and a little bit modified というやつですね。このグリーンエリプソイド is the file movement possibility will be changed, but when the landmark is detected, the possibility is become small. Without the landmark detection, this position estimation position is become widely. But once the landmark is detected, the two-dimensional position is the possibility will become more precisely. So therefore, the possibility will become the small. っていう、まあ、the present condition is like this. And some part is the preliminary prepared, and the scanning data is also matched to this the preliminary prepared three-dimensional map, and then the position will become modified while moving. このグリーンポジションが maybe the scanning present real-time scanning data and matching with the environmental map preliminary prepared, and then the correcting the position. ストップラインもなんかラインディテクションもやっていて、ストップライン is detected, and then the crossing this line. とかやってますっていう、まあだから2-dimensional scanner っていうのは very useful to make the environment and control the robot ですね。いう話です。はい。で、3-dimensional scanner は、まあ、not only the two-dimensional plane scanning, but also the 3-dimensional part is also added, and then this kind of laser measurement system for the landscape is detected. And also presently this is equipped on the drone system, and then some 3-dimensional map is developed like this. agricultural condition あっていきますか。キャストマイニングコンディション、あとディザスターディテクションです。ドローンが is used for the reconstructing mapping。もちろん DIC の3ディメンショナルスキャナーとか、他にもで RGBD カメラっていうのは RGB センサープラスデプスカメラね。デプスカメラ is also the widely used not only for the detection for the robot but also for example this kind of sensor is used for the gesture recognition for the operating the personal computers. Then, firstly, this kind of product is started by this the X-Chon sensor and the Kinect sensor by the Microsoft. Kinect version ASUS the X-Chon is here, and the Kinect sensor is like this and like this, and presently the Azure is the first version, new version, but it is only available in the USA and China, not in Japan. So therefore, I haven't used in the Azure Kinect sensor. And also the creative Senses 3D is based on the Intel chips, Intel RealSense 3D, and this is the latest version of the Intel RealSense. So we are using this kind of sensor type now. ちょっとこれプロモーションビデオとか見てみますか？ベースカメラ。
Intel RealSense depth cameras D415 and D435 with next-gen stereo depth technology and a dedicated low-power vision processor for real-time depth sensing. Gain flexibility with support for indoor and outdoor lighting conditions and long ranges. Higher image resolution and frame rates support accurate computer vision.
こういうのは all of these sensors is active vision だね。active projecting なんか撮ってるパターンで、and then the direct だから IR light is projected and the sensing by using the two cameras, and then the three-dimensional position is reconstructed.
The Intel RealSense D415 puts an Intel module and vision processor into a small form factor for development or productization, while the D435 is the same small form factor and provides a wider field of view and global shutter for capturing depth in fast-moving VR or robotics applications. With the Intel RealSense SDK 2.0, accessing the depth image, 3D point cloud, and configuration is easy. Integrate sample code to bring vision to your application faster. See how Intel RealSense depth cameras enable your visual computing project.
はい、これはインテルのセンサーですね。はい。で、final part is about the force sensor. で、force sensor は、フォースは まあこれなんですね。ホイーストンブリッジのストレインゲージ。まあ mainly they're using a strain gauge. Strain gauge means this kind of thin bar, and when the force is applied here, this bar is deformed. Deformed. This part is behind the part is pressed, and this front part is prolonged. So therefore, the resistance of this part is changed. The compressed, and this is tension is here, and the resistance is increased. But in this case, resistance will become decreased. So therefore, when detecting the resistance changing, and then this deformation will be detected. So many of the force sensor is using the mechanical deformation, and mechanical deformation is detected by the resistance change, changing its resistance. So therefore, maybe you in your high school days that you have learned about the Houston Bridge. Okay? 何ですか? Fixed resistance でここの this resistance is slightly changed, and then by using this bridge, the bridge circulation, circular bridge circuit, this slight changing is detected as the slight voltage changing, output voltage changing. And this two gauge method is this is the decreasing, 縮むだから decreasing resistance, and this is the increasing resistance. The two strain gauge is used as a pair, and then the output voltage will become the doubles. And then the 4 gauge type is the decreasing, decreasing, increasing, increasing. And then the 2 gauge, 2 pairs is used here, and then the output voltage becomes twice. 4 times. ですね。で、まあ、as a torque sensor, this deformation can be detected. The strain gauge type is the thin ball part is prepared, and then this thin pole is deformed, and then this deformation is detected as a resistance change. And also the magnetorestriction type is also here. The polarized magnet is changed, so the field sensor is detecting its polarization changing. And then the four-stroke sensor. Four-stroke sensor is used as a wrist sensor, for example. The gripping part is holding something and assembling something. And then so therefore this sensor is a wrist sensor is detecting the end chip, the end effectors force and torque. で、まあ this thin part is here, and strain gauge is plated, and also this is the crossbar is here, and this crossbar part is deformed. And this part, this type is the light type is also here. Light is emitted, and then the detection part is changing its position, and then the lighting power is changed. So the changing its light power is detected as a deformation. But the deformation is shown by this thin part. So therefore the force is applied here, and then by using this thin part, this part is deformed. So therefore the lighting condition will become changed. So by using this lighting condition is detected. これはストレインゲージタイプ。これはライティングパー、ライティングフォトディテクションタイプですね。Anyway, the outside and inside, some deformation will be detected. The mechanical deformation is detected. この outside part, inside link か、これは upper link, lower link で、strain gauge, the thin part is here by this thin part deformation is detected by strain gauge or something. This is the actual product. For example, as it said, the outside ring and inside circular and the crossbar is here, thin part is here, and the thin part, the strain gauge is attached, and then this deformation, this part of the deformation is detected by strain gauge. ですね。それは例えばこれ見てみますか。
Robotware Assembly Force Control from ABB and ATI Industrial Automation is a new robot option that will greatly facilitate the use of robots for assembly tasks. Assembly FC adds sensor feedback to allow the robot to search for the correct assembly position.
オレンジパートがセンサーですね。
Movement of the robot is force controlled. Forces and torques are measured by the sensor at the wrist of the robot. A measured force makes the robot react with a movement in the sensed direction, which acts to reduce the contact force.
カムシャフトのだから
This part of the
イン
video
サーションは
shows a camshaft inserted into a diesel engine block. The programming was not done to be time optimal, but rather to demonstrate the concept of force-controlled assembly. You can see that the robot is compliant, and with the help of a circular search pattern and an oscillating force, the camshaft will find its way in.
ここのコンタクトフォースをこのリスセンサーで測ってます。メジャーリングス by using this sensor ってやつですね。
In this part of the video, a half
ちょ
shaft
っと違うビデオ見ましょう。他にも BL オートテックとか、これはスモールセンサー for the fingertip each fingertip force detection のためのスモール、このダイヤメーターはここに書いてあるけど、ここに書いてある17ダイヤメーターとか18ダイヤメーターとか25ダイヤメーターとか、smaller size for the fingertip detection, for stroke detection sensor is also here. And this is the industrial type, also the Mita Corporation sensor. これ見てみますか。クラッチアセンブリングギアシャフトって書いてありますけど、このブルーパートがフォーストロックセンサーですね。このギアシャフトのそのギアの detecting the gear position and changing its orientation and then the insert っていうのをby using this the force stroke sensor。このアセンブリングタスクはこのギア4 part gear is the attached, so therefore finding the good position and orientation and then the insert っていうのをやってるってことですね。はい、おしまい。あとはなんだっけ、エプソンとかもセンサーもありますよとか言って、これみんなになんだジャパニーズなんでダメだよね。まあいいか。あとは時間があるな。まだ時間があるので、Which part you are interested in? あと説明してないのはどこですかね。そうです。例えばこれだ。ここのハイスピードビジョンっていうのは Maybe that you are interested in。なんだ1 millisecond visual feedback これは about more than 10 years ago で20 years ago か1 millisecond visual feedback system って at that time it is very dynamic アドバンストテクノロジー。
In this video proceeding, we describe our 1 millisecond visual feedback system and show a demonstration of high-speed target tracking. Our 1 millisecond visual feedback system uses a massively parallel processing vision system called SPE256, in which photodetectors and processing elements are directly connected. This allows our system to realize high-speed visual feedback. The processing element in the SPE256 system is a 4-neighbor connected SIMD-based parallel processor. It is compactly designed to integrate many processing elements on one chip. The processing elements are directly connected to the photodetectors as shown here. As photodetectors, we use 16 by 16 photodiode sensor array. The sensor platform has 2 degrees of freedom, pan and tilt, and its actuators are controlled at 1 millisecond feedback rate by the visual feedback information from SPE256 system. Next, we show high-speed
これ
target
モノキュラーだから
at 1
ホワイト
millisecond
ブラック
feedback
なんだけ
rate
ど、
using
ホワイ
this
ト
system.
ブラックパン
Here,
を
the
トラッ
target
キング
is
し
a
てるん
bounding
です
ball.
ね。
Our system has such good adaptability to the changing environment that we can even track the target when moving fast and irregularly as shown here.
And high-speed tracking is very important to realize this kind of tracking real time. And also this is
Next, we show
square.
intelligent target tracking by executing image processing algorithms on the 1 millisecond visual feedback system. For example, we execute the algorithm to extract the target among several objects. Then we can track only the target, in this case the square, as demonstrated here.
まあ、シェイプレコミッションというか、まあ、ティピカルフィーチャーレコミッション is also the realized ですね。っていうのは、まあ、これは例えばこれ今、about 20 years ago で、まあ、ちょっとスピードキャッチングで、afterward, some ball catching in the real time ボールのリアルタイムキャッチングとかね。これはキャッチングタイミングコントロール is very important to grasp at that time ということで、ハイスピードディテクション is necessary。これ、if you visit the 未来館 in Tokyo, this demonstration you can watch。お台場、ここにあるんです。こっちもちょっと見ますか。あと、by using this kind of technology, the hitting ball とか。
This video introduces an ultra high-speed robot as a milestone in the history of intelligent manipulation systems. Almost all robot systems are designed with a primary goal of the emulation of human capabilities and with less attention to pushing the envelope in terms of speed as mechanical systems. With the goal of making a robot whose movements are so fast as to be invisible to a human being, we have developed an ultra high-speed robot system which exceeds human capabilities. High-speed vision is the key technology that has contributed to the realization of an ultra high-speed robot. Generally, an intelligent system is composed of sensing, processing, and motor subsystems with their respective dynamics. To achieve optimum performance in real time, the total system should be designed by taking into account the constraints of the dynamics of each element. As viewed from the perspective of information flow, the sensor processing rate should be 1 kHz to realize stable control of actuators. In particular, the sampling rate of traditional vision systems is limited to the video rate of 30 Hz and is a bottleneck in terms of dynamics matching. Therefore, we begin with the development of a 1 kHz vision system.
This video is about 7 years ago.
Traditional vision systems are slow for direct robot control because they have an input-output bottleneck problem due to scanning and transmitting a large amount of image data. To solve this problem, we have developed a new digital vision chip architecture. In the vision chip architecture, photodetectors and parallel processing elements are integrated in a single chip without an I/O bottleneck. The parallel processing elements have general-purpose processing capabilities and are controlled by programs using digital circuits for real-time machine vision. Various visual processing algorithms such as moment detection and segmentation can be achieved within 1 millisecond because execution is in parallel. By loading the camera on a 2-degree of freedom mobile platform, the active vision system can pan and tilt to follow a fast-moving target and always keep it in view. Next, we developed a sensory motor fusion system by introducing the 1 kHz vision system. To achieve efficient processing and computational scalability for many kinds of algorithms, the system has a hierarchical parallel processing architecture and the flexibility to change its structure corresponding with environmental changes. In addition, each processing element has direct sensory inputs and direct actuator outputs to achieve dynamics matching with various speeds of sensory feedback. The hierarchical parallel processing model is designed to use sensory feedback not for servo control, but also for trajectory generation and task switching. As a result, the 1 millisecond sensory motor fusion system can become more adaptable and achieve dynamic motions such as grasping, batting, and throwing. In order to achieve more dexterous manipulation, we developed a new high-torque mini actuator and high-speed multi-finger hand with these actuators. The design of this actuator is based on the new concept that the maximum output power should be increased beyond the rated power output. In order to achieve high-gain feedback control, backlash can be removed with a harmonic gear. The newly developed high-speed and high-torque mini actuators are fitted in each finger link. The joint angles of the hand can be closed at a speed of 180 degrees in 1/10 of a second. The mass of the hand part is designed to be less than 1 kilogram on the assumption that the hand is mounted on the end effector of a manipulator. By integrating this high-speed hand and the high-speed vision system, we achieved various dexterous manipulations. These manipulations can be performed in the presence of unstable dynamic states with only a simplified model of the target object with high-speed motion. The concept of this project is to develop a high-speed robot with motions that are too fast for humans to clearly observe. That is, we aim at the speed limitations of mechanical systems themselves. We have developed the high-speed robot system based on dynamics matching. Moreover, target tracking, grasping, batting, catching, regrasping, dribbling, and folding have all been achieved at high speed. In the future, we plan to demonstrate new variations of skillful manipulation.
っていうビデオです。これユニバーシティ・オブ・東京のワンイメージプロセッシンググループのワークスサマライゼーションですね。石川ラボです。はい。じゃあ、that's maybe the time is also over. So therefore the